In this video, we're going to talk a little bit more about organic structure and organic functionalities. So if we look at one of the compounds we've talked about before, propane, we know that propane has the formula C3H8. There's a couple ways that we can represent the structure of propane. I can draw this as a written out formula, so I can write this as CH3, CH2, CH3. I can draw this with the bonds represented as lines, so I can have H3C with a bond to a CH2 with a bond to a CH3. I can even represent the hydrogens with the bonds drawn to them if I want to be even more specific about the bonding and represent the sp3 hybridized nature at each carbon center. So I can draw each carbon-hydrogen bond. Or as we saw in the last video, we can draw this as a structural formula by just having something that looks like this, where we understand that each one of these points represents a carbon that's filled in by hydrogens. So if we look at propane, there's really only one arrangement of atoms that we can have. We can only have a CH3 connected to a CH2 connected to a CH3. There's no alternative structure we can have. However, let's look at one more carbon chain length, which is butane. So the structure for, or the formula for butane is C4H10. I can write this as CH3, CH2, CH2, CH3. And I'm going to skip these middle two structures. I'm going to draw the line structure or the skeletal structure. So I have a CH3 connected to a CH2, connected to a CH2, connected to a CH3. However, this is not the only structure of butane I can draw. In fact, in the last video, we saw that there's different ways we can arrange four carbons in space connectivity-wise, such that we have the same formula, we have the same overall formula, C4H10, but the atoms are connected in a different way. So if we imagine for a second, taking this carbon here, this CH3 group, and instead of connecting it to this carbon here, we would instead have a structure that looks like this. So we have a CH3 connected to a CH, connected to a CH3, with another CH3 pointing directly up. And if we were to write out the formula, so we have CH3 connected to a CH, connected to a CH3, connected to a CH3. If we tally up all of the carbons and hydrogens, we see that we still have 1, 2, 3, 4 carbons. So we're still at C4. And we have 3, 6, 9, 10 hydrogens. So we still have the same formula, but we've changed the connectivity of the atoms. So when we change the connectivity of the atoms but have the same formula, we have what's called constitutional or structural isomers. So what this means is the connectivity of the atoms in the molecule are different, but the overall formula remains the same. So we're still at C4H10, but we've changed the connectivity from this linear structure to this branched structure, and that gives us the constitutional isomers of butane. So we see that we have two, we would say there's two constitutional isomers with the formula C4H10. Now, as we add more carbons, or as we introduce various functional groups, which we'll talk about at the end of this video, we can imagine that there's more and more constitutional isomers that appear for any given formula. So let's look at one more. So let's look at pentane. So pentane has the formula C5H12. And if we draw this as a linear structure, again, I'm not going to write out the structural formula. I'm going to draw out the skeletal structure. So I have C1, 2, 3, 4, 5. So this is our linear structure for C5H12. And if we count the carbons, we see we have 1, 2, 3, 4, 5. So we're at C5. We have 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 hydrogens. So we are at C5H12. Now, how would we go about drawing the constitutional isomers of pentane? This would be the most, probably the first structure you would notice. for C5H12. And then what we're going to do when we're drawing constitutional isomers is we're going to take various portions of the molecule and, like Legos, we're going to pop them off and stick them on other portions of the molecule. So for instance, I can imagine taking this CH3 and moving it from the terminal position to an internal position. So I go from a 5-carbon chain to a 1, 2, 3, 4 carbon chain. We have 1, 2, 3, 4, and I've then moved this CH3 to this position. So this is a constitutional isomer of pentane. We would call this neopentane, or isopentane rather. We call this isopentane. We still have C5H12, but we've rearranged it so we have a different arrangement of atoms. So we see in this case we have a 5-carbon chain. In this case we have a 4-carbon chain. Note that if we were to draw something like this, at first glance these look different. However, we see that if we rotate this 180 degrees, we would end up with something that looks like this. Oh, excuse me, I drew that a little bit wrong. We would end up with something that looks like this if we rotated it 180 degrees. So this would come all the way around to here. And these two structures are going to be exactly the same. So this is not a constitutional isomer of pentane. We've already drawn the only 4-carbon chain that is a constitutional isomer of pentane. The next best guess would be to draw a 3-carbon chain. So we have a 3-carbon chain. This is our propyl chain. And note, we still have 2 carbons left to place. There's a couple different options. Note, if we put it at the end, then we're left with a 4-carbon chain, which we've already drawn. So that's not going to be where we place our 2 other carbons. And if we think about it, the only other place we can place our 2 other carbons are on this middle carbon, this internal carbon. So we count, we have 1, 2, 3, 4, 5 carbons. We have 12 hydrogens, so we are still at C5H12, but we have now what's called neopentane, which is the 3rd constitutional isomer of pentane. So we have a 5-carbon chain that's an isomer, a 4-carbon chain that's an isomer, and a 3-carbon chain that's an isomer. And these would be the 3, we would say these are the 3 isomers of, or specifically the constitutional or structural isomers of pentane. So let's look at an example where we would have something more complicated, something with heteroatoms. Heteroatoms meaning not carbon or hydrogen. So let's look at C4H10O. And the question is, what are the constitutional isomers of C4H10O? And I'm going to tell you off the bat that there are 7 isomers. And if you want to pause this video and kind of think about it for a second, this is where I would pause the video to kind of draw these out. When we're looking at heteroatoms, there's a couple of things we want to think about. Now, we've already seen that carbon likes to have 4 bonds to it. Every time we're going to draw a carbon, we're going to have 4 bonds to it. But we can do this for heteroatoms as well. Nitrogen prefers to have 3 bonds. Oxygen or sulfur prefers to have 2 bonds. And halogens, which is Cl, Br, F, or I, more commonly just abbreviated as X, are going to have 1 bond to them. So if I'm looking at this O, I know that every time I draw this O, it must be attached to 2 other atoms in the molecule. So let's start drawing the isomers. And if you want to pause having known this and draw the isomers, this is where I would pause the video and try and figure out what the 7 isomers of C4H10O are. But we can draw these together. So the way I would do this is start with the easiest structure, or the simplest structure to think about, and that would be a linear 4-carbon chain with an oxygen tacked on at the end. So I have a linear 1, 2, 3, 4 carbon chain, and then I have an O, and remember O must have 2 bonds to it, so I'm going to put an H. If we count to make sure we have C4H10O, we have 1, 2, 3, 4 carbons. Here's our O over here, and then we have 3H, 2H, 2H, 2H. That would give 3, 4, 5, 6, 7, 8, 9, and 1H makes 10. So this is a valid constitutional isomer of C4H10O. Now, just like when we're moving around like Legos, the structures of various pieces of the structure up here, I'm going to take this OH, and to generate another constitutional isomer, I'm going to take it off this 4 carbon and put it on an internal carbon. So what would that look like? Again, we would have the 4 carbon chain, 1, 2, 3, 4, except now we have an OH on an internal carbon. And again, we could check this structure to make sure that C4H10O. So we can move this OH in order to get a new structure. Now, keep in mind, if I put this OH instead of this carbon, I put it on this carbon, we would have the same structure in a similar fashion to what we had up here. We could just rotate this 180 degrees and we would get the same structure out as we did with this one. So this is the only this is the second 4 carbon chain with an OH that we can establish as a constitutional isomer. Since these are the only 4 carbon chains we can do, let's then look at what a 3 carbon chain would look like. So we have a 3 carbon chain, and I can't put that 4th carbon at the end, so I'm going to put it in the middle. And now we have options. Where would we put our OH? I think the easiest next option to do would tack on this OH at the end. But equally as likely, instead of putting it on the end, we could put it on an internal carbon. So another structure we could have would be the OH tacked on to an internal carbon, that apical carbon in the center. Keep in mind, just like before, if we took this OH and we put it here or here, we would simply have the same structure and we could rotate that 120 degrees to see that we get the same structure out as we did before. If we think about it, these are the only 4 structures where we would have an O attached to a carbon and a hydrogen. We can try playing around and see if there's any other places we can move this OH and tack it on in various different locations to see if we can get another constitutional isomer. But you'll see that these are the only constitutional isomers with an OH. However, O only needs 2 bonds to it. This is a carbon with a carbon and a hydrogen bonded to O. But what if we had a carbon and another carbon bonded to O? So, for instance, I could take 1, 2, 3 carbons and then tack an O in the middle, and then put another carbon on the end. If we check this structure, we have a CH3, a CH2, a CH2, and a CH3. If we're counting carbons, we have 1, 2, 3, 4. There's our oxygen. And then we have 3 hydrogens, plus 2 is 5, plus 2 is 7, plus 3 is 10. So this would be a valid constitutional isomer of C4H10O. And after this, we simply start moving where this O falls. So in this case, we have 3 carbons on one side and 1 on the other. But we can imagine where we have 2 on one side and 2 on the other. If we moved it 1 over and we have 1 and 3, we would see that it's the same structure as the first O double bonded to C that we had. So these would be the 2 structures where it's linear. But we can have a modality that looks something like this, where it's branched, where instead we have something like this. Then we have an O here and another carbon. Now I couldn't put it in the center because O, based on its valence, will have 2 bonds to it. So if I put O in the center and it had 3 bonds to it, we would check the formal charge and we would see that it would have a plus charge on the oxygen. When we're drawing constitutional isomers, we want to avoid drawing structures that are unfavorable. So this would be the last favorable structure. And here are 7 constitutional isomers of C4H10O. And you can do this type of plucking off and moving over and rearranging what's bonded to it for any type of constitutional isomer problem that you encounter. For the last part of this video, I want to talk about functional groups. So functional groups, we've already seen 3 of them. We've already seen C single bonded to C. This is called an alkane. C double bonded to C. This is called an alkene. C triple bonded to C. This is called an alkyne. So we've already seen 3 types of functional groups. Now these may not look like functional groups, but they indeed are. If we saw a C double bond to C, we'd say, okay, this molecule has an alkene in it. Now most functional groups are going to contain some kind of heteroatom. So that's usually O, N, S, or a halide. So let's go through the common functional groups that you'll see in this course and discuss the name for them. So the ones we've already seen are OH or ROR. So, or rather, I guess in the structural drawing as I did before, instead of OH you have OR. OH, we call this an alcohol. And an OR group, where you have an O between two carbons, we call this an ether. So the structures we were drawing for C4H10O were alcohols and ethers. Remember, C is going to be O is going to be having two bonds at any given case. So there's a couple different variations of O having two bonds to it, in this case, doubly bonded to C. So we can imagine we have R, C, double bonded to O, R. If we have a C double bond O in between two R groups, R meaning these are alkyl chains, alkanes, alkenes, alkynes, we would call this a ketone. If we were to change one of these R groups to an H, we call this an aldehyde. If we change that H or that R group to an OH, we call this a carboxylic acid. Acid because this H makes it a Bronsted-Lowry acid. These tend to have pKa's of around 5. If we instead change that OH, H, or R to an X, meaning a halide, we call this an acyl halide, and that halide is replaced with whatever it is. If the X is a Cl, we would call this an acyl chloride. If it's a Br, we would call it an acyl bromide. If it's an F, we would call it an acyl fluoride. And if that is not an X, an OH, an H, or an R, but it's an N with two groups, this R can be either alkyl groups or hydrogens. We call this an amide. So these are the typical functional groups that are going to be containing oxygen within them. Ones that contain nitrogen, if we have a CN, we call this a nitrile. If we have an NR2 by itself, similar to this amide down here, if we have an NR2, again, these R's can be R's or H's. We call this an amine. And if we have an NO2, this is a less common functional group, but one you see if you continue on in organic chemistry, we call this a nitro group, or by itself, we call this a nitrosol group. Probably the least common one you'll see in this class, but more common if you continue on in organic chemistry, is sulfur-containing compounds. If you have a terminal SH, similar to the OH over here, but now it's a sulfur, we call this a thiol. And if you have an SR, so it's now S bonded to two carbons, we call this a thioether, or more commonly a sulfide. So these are going to be the functional groups that you're looking out for. I know that the homework has some that you're going to be naming them or identifying them, but it's good to be aware of most of these functional groups so you can have a common vocabulary to talk about different functionalities in a molecule when we're building molecules in organic chemistry.